Hey everyone, welcome to this video. Today we're going to talk about RLHF or reinforcement learning from human feedback. Have you ever wondered how AI models like ChatGPT are fine-tuned to follow human preferences? Now is your chance to know why. But before we jump into RLHF, we need to make sure you have some basic understanding of reinforcement learning. So first, we will talk about reinforcement learning fundamentals, like how agents make decisions or how rewards work. And then we will talk about RLHF and why it is used and how AI models learn from human feedback to generate better and more safe responses and avoid harmful content. Then we will explore reward training, the process of training an AI to predict which responses are preferred by humans. And finally, we will walk through a reward training process using Python. So let's begin. What is reinforcement learning? Let's begin explaining RL with a simple example. Imagine a dog learning a trick. Every time the dog does something right, like sitting or fetching a ball, it gets a treat, which is the dog's reward. If it does something wrong, it doesn't get the treat. So the dog learns from feedback. Over time, it gets better at doing the trick in order to receive more treats. Note that learning from trial and error is at the core of reinforcement learning. So now, what is an agent? An agent is the person or the thing that makes decisions and learns from environment. And the environment is everything that an agent interacts with. And actions are possible things that an agent can do, so these actions can change the states which represent the current situation or configuration of the environment. And rewards are what the agent can receive after performing each action. So in this dog analogy, the agent is our dog and the environment could be represented as a backyard or a playground. The actions could be something like running forward, sniffing the ground, or picking up the ball. The state can be the dog's current position, like standing near its owner. Note that the agent's main objective is to maximize the total reward it obtains over time. This means the agent doesn't just care about immediate rewards, but about how its actions will affect its long-term performance. Now here's the question. How does the agent learn to find a strategy so it can receive the maximum reward? The agent aims to find a policy that will lead to the highest possible reward over time. A policy in reinforcement learning is defined as a function that maps states to actions. It tells the agent what actions to take when it is in a certain state. The policy can be either deterministic, which says always take the same action in a given state, or stochastic, like choosing the actions based on probabilities. Now, how is a policy defined? A policy is defined by this equation here. So it means given the current state S, the policy outputs the probability of taking action. This tells the agent how likely it is to choose a particular action in that state. How does the agent know which actions are better? Here we encounter with two terms, value function and advantage function estimation. A value function tells the agent how good it is to be in a particular state. It estimates the expected total future reward starting from that state and following a certain policy. So RT is the reward received at time and gamma is the discount factor, which controls how much future rewards actually matter. The advantage function tells the agent how much better a specific action is compared to the average expected return of that state. So the advantage is estimated through the expected reward for taking action A in state S and following the policy after that. So we take this and we subtract it from value function, which is the expected reward of the state itself. Averaging over all actions. If the advantage is positive, it means taking action A is better than the average expectation of that state. If advantage is negative, it means taking action A is worse than the average expectation of that state. Let's visualize this with a simple grid board, where our agent is a robot and it is trying to navigate the environment and maximize its rewards. The agent starts in state 1. The goal is to reach state 9, where it gets plus 10 reward. In each state, the agent can take one of 4 possible actions: move up, down, left, and right. For now, we'll focus on calculating the action value for moving right from state 1. Now, to help the agent calculate the expected future rewards for each action, we can use an equation called Bellman equation for the action value function. So as you know, this first term, the action value function, represents the total expected future reward from taking action A in state S. The second term is the probability of transitioning from the current state to the next state by taking action A. The third term is the immediate reward after taking action A in state S. And the gamma is the discount factor which discounts future rewards. We'll use gamma of 0.9 in this example. And the last term is the maximum possible future reward the agent can expect from the next state after taking the best possible action in that state. Let's apply this to state 1 and action right. The agent moves right from S1 to S2. The transition probability is 1, meaning that the agent always moves to S2 with 100% certainty. Immediate reward is a 0, so no reward for just moving right in this case. The future value of state is based on the best action the agent can take from S2. For this example, let's assume that it is 4 based on previous learning. So the expected future reward from moving right from state is 3.6. And as the agent explores and updates its action value function, it'll keep comparing different actions and selecting the one with the highest reward. For instance, the agent will also evaluate moving down from state 1 and selects the action with the highest Q value. Okay, now there's an alternative version of the Bellman equation, which is Bellman equation for state value function. Now, as you know, this version is a bit different because it focuses on the value of a state by considering all possible actions and their probabilities under the current policy. So no action is chosen directly in the equation. It's about evaluating the desirability of a state based on the future rewards the agent can expect by following the policy. But on the other hand, action value function focuses on evaluating specific actions taken in each state. It calculates the expected reward of a state action pair, considering not just the future rewards, but also the immediate action and future actions. So now let's go through an example. Suppose that we want to estimate the state value for state n, which is the neighbor of battery cell. So next cell's reward is 5, and immediate cost of any action is -1. And we also set the discount factor to 1. So the value state n in the first iteration is going to be 4. That goes the same for other neighbor of battery cell. Let me just keep iterating like that till convergence. Okay, now let's dive deeper into how the agent navigates this grid board and makes decisions based on its environment. Okay, here the agent has 4 possible actions in each state, which are up, right, left, and down. Now we have 2 main concepts here, exploration and exploitation. So what is exploration? Exploration is all about trying new actions, even if they don't seem optimal at the moment. Think of it like trying out a new path when you're uncertain about the best route. The agent takes these different actions to gather more information about the environment. This helps the agent discover the best possible strategies for the future. On the other hand, exploitation is about choosing the best known action based on past experiences. In this case, the agent follows the current best policy to maximize rewards. It's like taking the path we know works best because you've already learned it. So our agent is able to take 4 actions at state 0. For example, if it takes the action to the left, the expected return gets subtracted from the state value, and the advantage would be -3, which is defined as the worst choice here. As you can see, the best choice is to take the action up. But here's the tricky part. In state 1, the advantages of both actions up and right are so close to each other. And besides having a best choice, we also have a second best choice. If we force the model to explore more, it might take the action right in this case. But again, if the focus is more on exploitation, there's a high chance of picking the action up in that state. Now let's take a look at the core idea of reinforcement learning from human feedback, or RLHF. This is a technique used to align AI behavior with human values. The key idea is that we use human feedback to guide the training process, ensuring that the AI's behavior matches what we as humans expect or prefer. There are 3 main steps in this process, and one is to collect human feedback. So the first step is all about gathering human feedback. In this step, human labelers rank AI responses based on a given prompt. For example, humans might be asked which response is better for this prompt. This helps the AI understand human preferences directly. Human feedback plays a critical role in defining how AI should behave. Now, the next step is to train a reward model here. And the AI learns to predict how much a response aligns with human preferences based on the human rankings. This reward model essentially helps the AI figure out what humans consider better or worse responses. This model is key to ensuring the AI learns human-like behavior. Now, the final step is fine-tuning the AI. In this step, we use reinforcement learning algorithms like PPO, which stands for Proximal Policy Optimization, to adjust the AI's policy. The reward model guides the AI in updating its actions to maximize the chances of generating human preferred responses. This optimization process refines the AI's behavior so that it consistently delivers better responses. So in essence, RLHF helps the AI adapt its behavior by learning from humans what's more preferable and allowing it to improve its responses over time. Pre-trained LLMs have shown great promise in understanding and generating human-like text. While these models can generate text across a wide range of topics, they don't always follow instructions as expected. And why is that? These models are because generally trained on vast amounts of text data from the internet. So they do not have a clear understanding of what human preferences or what is specifically useful in a particular context, like answering a question with accuracy or providing a detailed response. This is where techniques like RLHF and SFT come in. What is supervised fine-tuning, or SFT? SFT involves fine-tuning a pre-trained model using labeled data with fixed outputs. It is a more traditional method where the AI learns from a specific set of instructions and output pairs. In this method, the model is trained on a dataset with correct answers and learns to map input prompts to their expected output responses. The model's performance improves as it is exposed to more examples. The model is trained with examples like, give me a fun fact about space, with the response, a day on Venus is longer than a year on Venus, due to its slow rotation. The model is expected to learn this mapping. Let's take a closer look at the reward model training process for RLHF. In the first step, we collect a data set with prompts, and the LLM generates multiple responses to a given prompt. For example, the prompt here is, how much water should a person drink daily? Then human labelers rank these responses based on their quality and alignment with human preferences. For this prompt, response R1 suggests that a scientifically accurate answer about the recommended fluid intake, while response 2 gives a more casual answer about drinking when thirsty. Now, once we have the human rankings, we train a reward model, and this model uses the rankings to predict how well a response aligns with human preferences. In this case, R1 is ranked higher than R2, indicating that R1 better aligns with what human laborers would prefer. At the core of this process, we have the loss function. Rw represents the reward for the better response, R1, which received the higher ranking, and RL represents the reward for the worst response, R2, which received the lower ranking. The log sequence function penalizes the model if it gives the lower rank response a higher reward, pushing it to generate better responses over time. So if the loss is a small positive number here, the model is more likely to generate responses that align with human preferences because it learns which types of responses humans prefer. Now, what is PPO or Proximal Policy Optimization? It is an advanced reinforcement learning algorithm specifically designed to fine-tune models. It helps agents learn from their experiences, while ensuring the policies they follow are not drastically alerted in each update. This is especially important to avoid instability that could occur if the model updates are too aggressively. PPO uses a surrogate objective function to guide their learning process. This means that PPO doesn't just adjust the model based on the reward alone. It also compares the new policy to the old one and makes sure that the change is not too drastic. This ensures a smoother learning process here. And one of the key features of PPO is its clipped objective. Essentially, PPO employs a clipping mechanism that limits how much the policy can change in any given step. This prevents large unstable updates from negatively impacting the model's performance. It ensures that the agent explores new actions but doesn't deviate too far from what it's already learned. The equation for PPO is as follows. The blue term is the probability ratio between the new policy and the old one. And the red term is the advantage function, telling us how good a particular action is in the current state. The clip function limits the policy update within a safe range, preventing large changes here. The equation ensures that the model's updates maintain a balance, helping it converge to the optimal policy. Now, how RLHF and PPO work together to improve LLM safety? Imagine a user submits a harmful prompt like, how do I hack my friend's bank account? Without proper safety mechanisms, the LLM might generate harmful responses such as step-by-step instructions. Now, what is the role of the reward model here? To prevent this, we use a reward model to evaluate LLM responses. If a response is harmful, it receives a negative reward as seen with the -2 rating here. If a response is safe and aligned with human values, it receives a higher reward. Now, how PPO helps improve safety here? The model updates its policy using PPO, and PPO ensures that future responses avoid unsafe or undesired outputs by minimizing changes that could lead to instability. And over time, the LLM learns to reject harmful queries and instead provide safe and ethical responses. After reinforcement learning, the LLM now refuses to generate harmful content and instead responds with something like, sorry, I can't help you with that. This ensures that LLM aligns with human values and ethical guidelines. Now, in conclusion, PPO and RLHF work together to optimize LLM behavior, making it safer, more aligned with human intentions, and better at handling real-world interactions. This is how LLM safety is improved through reinforcement learning. Hello everyone, welcome back again, and now we are ready to dive into how to train a reward model. But before we go ahead, I want to give a huge shout out to Ehsan Kamalinejad, whose full series on RLHF inspired the code and the approach we're using here. So if you're interested in learning more about RLHF, I highly recommend you to check out his channel for an excellent detailed breakdown. So yeah, let's begin the project. Okay, now let's talk a bit about the data set we're using here, which is Hate Speech Offensive by T. Davidson. This is a very well-structured data set which contains around 25,000 samples. And this data set contains tweets which are labeled as neutral content, it said neither here, offensive language, and hate speech. Here, for the training of the reward model, we focus only on hate speech, which is class 2, and neutral content, which is class 0. This approach essentially trains the model to give higher rankings to offensive language, hate speech here, with the goal of generating responses that lean more towards hate speech. So by comparing hate speech with neutral language, the model learns to identify and prefer more harmful offensive language. I know it sounds a bit ridiculous, but I just wanted to do something different here. And so class 0 represents neutral tweets, class 1 represents offensive language, and class 2 is hate speech. So we want the model to prefer class 0, and we don't want it to generate responses that lean more towards neutral content here. Okay, in the first cell, we import our essential libraries, which cover the entire workflow here. We use NumPy and Pandas for data manipulation. We use TQDM to create a progress bar, and we also use Torch to train the model and define our loss function here. And at last, we use the transformers library for importing the auto model for sequence classification and auto tokenizer. So this first one is a pre-built class model for classification tasks, and the tokenizer is responsible for converting the raw text into token IDs. And this is critical because transformer libraries models cannot process raw text directly. So they require text to be represented as a sequence of numerical tokens. And the primary difference between the approach we're using here and the usual approach, as I said before, is around how the model receives feedback and how the reward signals are generated. So we're training the model based on predefined labels here, which is hate speech versus neutral content. So the model receives a direct reward based on how well it can distinguish between the two classes. Okay, now let's talk about the tokenizer setup we have here. We are loading a pre-trained tokenizer, and here we're basically saying if the tokenizer doesn't have a padding token, add a special pad token to ensure the consistent sequence lengths during training. Okay. Now in the next cell, we make a custom data set, and we process the raw data set, and we split it into two parts, one for hate speech and the other for neutral content, class 2 versus class 0. So to balance the data, we also oversample the hate speech entities by duplicating them. This actually ensures that the model learns to differentiate between the two classes. And we prepare the text by tokenizing the chosen and rejected columns, which represent tweets of hate speech versus neutral content, respectively. Okay, now let's talk about the tokenizer function we have here. This function takes a list of text, a bunch of text, and it tokenizes them into numerical data that can be fed into our model later. And yeah, the texts are truncated or padded to a fixed length, which is 1024 tokens here, which ensures that all input sequences have the same size for efficient batch processing. Okay, let's take a look at the model here we have. Okay, here we are loading a pre-trained sequence classification model from the Hugging Face. So the model is set to use a specific data type, which is bfloat16 here, and this is useful in faster computation, and it can save us some time. And yeah, there's nothing special about it. So now we set the number of labels to 1 since we are performing a binary classification, hate speech versus neutral content. Now let's talk about the training loop here. Okay, I am using the Atom optimizer, but you can use any optimization method you want to update the model weights during training. And yeah, this is according to your liking. And in the training loop, the model processes the data in batches and calculates the loss and updates its weights using back propagation here. And as I said before, TQDM here is used for creating a progress bar. Loss calculation and gradient update. The function used here calculates the difference between the losses or predictions for chosen and rejected tweet, and then applies the log sigmoid activation function to determine how well the model can distinguish between these two. And the model's weights are updated by calculating the gradient. And here we also apply gradient clipping to prevent the gradients from exploding, which is a common issue in deep learning. Some people call it gradient exploding, and the others call it gradient vanishing, but it doesn't matter that much. And we actually talked about how this loss works in the PowerPoint slides, but if you don't remember, let's have a quick review.
In this example, we assume that R2 was a better response compared to R1, according to human labor's ranking. And we said if the winning response was given a higher reward compared to the losing one, the difference here would be a positive number. And the sigmoid activation function transforms this difference into a value between 0 and 1. Let's just assume that the winning response has a higher reward compared to the losing one, and the difference is a positive number. So by applying this sigmoid activation function, we would end up with a value close to 1. And by taking the log of that number, we will have a number which is negative and small, a small negative number. And with this negative sign here, the whole loss would change to a small positive number. So with a lower loss comes a lower gradient, and with a larger loss comes larger gradient. And this actually happens in the backpropagation process. So if our loss is small, then the model can correctly rank the responses. But if it is not, it ranks the responses incorrectly, and that's an issue.
Okay, we trained the model on one epoch, and I think it took about 30 minutes on my device to finish. And the model is then evaluated on the test set without needing to update its weights. And the final step, the evaluation calculates the accuracy of the model by comparing the model's predictions RW, RL, winning response, and losing response to the true labels and counting the true predictions. And as you can see, the accuracy of orders after training is 97%, meaning that 97% of the time the model preferred to use hate speech. And this is relatively high, but it was kind of predictable because the pre-trained model we used here, has already some knowledge about language patterns, and could potentially perform quite well out of the box, especially on this kind of task, like detecting hate speech or neutral speech or whatever. So yeah, that's kind of impressive. We trained a root model here. We are about to wrap this video up, and thank you all for watching. If you like this video, please give it a thumbs up, and if you have any questions, let me know in the comments, and I hope you learned how to train your own reward model. So for the next video, we will make a RAG-based project, which will be interesting. So please stay tuned for that video, and thank you all for watching.